Hey class, just a short quick lesson about a couple things today. Um, One, I want to talk about banked turns and how that relates to our whole idea about centripetal force. Um, if you remember, any time something is moving in circular motion, it requires an inward force. So for a banked turn, like you see here and here, here and here, for race cars, even some kind of certain types of bicycle races in the Olympics, you'll see banked turns, turns that are on incline. Now, it might seem kind of in your mind why that's obvious helpful, but let's talk about the physics of why that's actually helpful. So let's first take this car here sitting on level ground. Sitting on level ground, the car has weight that pulls it down. It also has the normal force from the ground pushing it up. So weight, it's force of gravity, means the same thing as force of gravity, pulling it downward, and the normal force pushing it upwards. The car is not accelerating up or down. Those two forces are equal to each other. The normal force kind of supports the weight. Now remember what the word normal, why we say normal. That means perpendicular. This acts perpendicularly to the surfaces that are in contact. Okay? Now, that's always the case, regardless of how the surface is. So consider over here now a car that's on an incline. And that car still has weight that is pulling it downward, and that weight must be supported. Okay, but now the normal force is still normal, but it must be perpendicular to the surface. Sorry about that. So that's perpendicular. So part of that now is pushing inward. So here is your normal force. And now that force isn't just going upward, it's going upward as well as inward. The center of the circle is over here, and it has two components. It has a vertical component that still cancels out the weight. So it has this. Remember when we talked about force components? And it also has this inner component. We could have drawn this triangle the other way if you want. But this inner component provides for us the centripetal force. Right now we're kind of just ignoring friction because that complicates matters for right now. But when we have our normal force here, it has a y component and an x component. And so because it's not just friction keeping us in a circular path anymore, which friction is always present, it is also the inward portion of the normal force. So the ground is actually physically, the ground is pushing you in like this. Because of that inward component, that is a center seeking, that is your centripetal force. Combined with that is also friction. Okay, so like I said, we're kind of ignoring friction right now, but friction is also, the car wants to kind of go tangentially, so friction also pushes the car inward. So the speeds that you'd encounter on a NASCAR race like this, 180 miles per hour or so, if this were on a flat ground, the car is just simply not going to be able, the friction between the car's tires and the road, it's not going to be able to keep that tight of a turn because the friction that's pushing it inward and kind of down the ramp here would not be able to hold it. But when you have both friction and the normal force, the track itself pushes you inward. Think about that bucket that I always talk about swinging inwards, or swinging in a vertical circle. If we kind of swing it in a horizontal circle instead, this is like the bottom of the bucket acting on the water. It's just pushing it inward. When a car, if you look over here, is traveling on a circular path, it needs this inward force. These guys here always has to be acting. And for a car on a banked turn, this force is a combination of that inner center-seeking portion of the normal force, as well as the friction that acts inward. Friction's not going to be enough when you're going really fast on a really tight turn like that. So the ground itself pushes you inward. Okay, so again, simply by changing the incline of the road from this to an incline, the road now pushes you that way, or rather, and this has that inner component to it. Clean some of this up a little bit here. So here's another graphic that kind of shows the same thing. Here's your car in an incline. Force of gravity pulls downward. The normal force pushes upward. And you see those two components of the normal force a little bit more neatly than I was drawing them before. So your X component of your normal force and your Y component of your normal force. This supports the weight of the car. This pushes the car inward. Alternatively, if we look at that same instance and we have friction, this is how it kind of breaks down. We still have all this stuff from the normal force, but static friction pushes the car down the ramp, and it's actually kind of pushing the car downward as well as inward. So this guy and this guy add together to create your centripetal force. Your net centripetal force is going to be the sum of all of these. The X component of your frictional force and the X component of your normal force. If there's no banked turn, it would just be that, and that would not be enough for really high speeds on a tight turn. Now, these types of problems can be a little bit complicated for us when we start including friction, because you gotta do angles and sine and cosine and all that kind of stuff. So I want to come at this from more of a conceptual perspective. So so that you guys understand what the benefit of the banked turns are. So the last few things I wanted to do on this video with you guys is do a couple different problem types. I'm referring to your packet, so I'm looking at letters G and H on page 10 of your packet. Since we were talking about banked turns, if you want to refer to J on that same page, here's a problem that kind of incorporates that same thing. I don't know if we necessarily need to do this, but I wanted to show you this, is that if we wanted to solve a problem like this, we could certainly do so by, the force of gravity is going to be the weight, so mg. This guy is also going to be mg because it has to balance that. And F net, that means your FC, which would just be equal to mvt squared over r. So we have mass, we have vt, and we have radius, so we can certainly find that. Now remember, that needs to be from the way that this picture is drawn. That's inward as well as this force. Now, the tricky part of this particular problem is that this force here, didn't mean to skip slides. Sorry about that. Of this force here is that when you do that math, that comes out to be a little over 8,900s. It comes out to 8,935. Now that force, this centripetal force, since there's no friction, is the centripetal force, which is the Fx. So that value down here for F net is also this value down up here. And when you know that, you know this force because that's equal to the weight, you know this. So from that, you would then need to find the angle, and once you have that, you can then find the normal force. And you start getting into trigonometry and stuff like that. But I don't know, if you guys are bored or something at home, I'll just be very quick here. This number comes out to be 11,760 newtons. So if you Pythagorean this number and this number, this is the hypotenuse of those two things, and that comes out to be 1,4,769 newtons. Sorry. Weird drawing with the mouse. 14,769 newtons. Excuse my sloppiness. Let's set that up a little bit. And so you have the three sides of this triangle. 1, 2, 3 at that point, and then you can find the angle of 53 degrees using really any of the trig functions at the other side. Maybe use tangent since you first had the fy and the fx. I'm not going to test you for problems like that, but it's just interesting to connect that there as well. And if we want to know the centripetal acceleration, that just winds up being around 7.5 meters per second squared. Easy way to do that is just take your centripetal force and divide the mass of it. So you just divided this number by 1,200 kilograms. That gives you your acceleration, because remember, net force is equal to mass times acceleration. So acceleration is equal to net force, in this case the centripetal force, divided by the mass. So like I said, there is, I'm not going to quite quiz you over this, but it's nice to connect there. And again, think of this as the race car I had on one of those previous slides. Remember, this is our centripetal acceleration. That's the g's that they're feeling. So this isn't very fast. But as I make note of on the other slide is that some of these race car drivers, when they're going around the turns, which is a good portion of their race, they're feeling upwards of, 3 times the acceleration of gravity, 3 g's. So, 3 times 9.8 is what, 29.4 meters per second squared. So if it's a 150-pound driver, it feels like they weigh 450 pounds during that entire turn, which is certainly not comfortable. It's hard to breathe. It's hard to hold onto the steering wheel. It's hard to do the other things that a driver needs to do during that time. So it's important to kind of look at that conceptual aspect as well. And that, so if we go back to this slide, that force, those are all the g's. There's that centripetal acceleration going inward, and that's what they're feeling. They're feeling very heavy. They feel like they're getting forced down into their seat, but they're actually getting forced that hard inward. Really, I guess it's upward like this, but the inward component of that is what's providing the centripetal force. Okay, so the other problems I wanted you to do, we'll do together here, are letters G and H. And these are the ones that I am going to ask you guys to do a few examples for here, especially this guy. I'm not sure if there's another example of this, but definitely you want to know how to do both of these. And again, these are on page 10 of your packets. All right, let's first tackle G here really quick. So you have a 900 kilogram car, makes a horizontal turn at 15 meters per second. So that's our VT. Up here is our mass around a curve with a 32.5 meter radius of curvature. Okay, as always, your force of gravity. Okay, there's no banked turn. We're just on flat ground here. So your force of gravity is just going to be mg, 900 times 9.8, which is, when you do the math there, it comes out to be 8,820 newtons. Your normal force, okay, we're not sinking to the center of the earth, so your normal force needs to match that. And so that's going to be the upward force from the ground. So that is also 8,820 newtons going upward. So, as has been the case in a lot of these problems, the net force is your centripetal force. So you find, to get that, that's when you do the M times VT squared over R. Sorry, you're probably hearing my daughter in the background there. She's just playing. And so when you do MVT squared there, that should get you 6,230 newtons. And that has to be inward, so the direction looks like that. And that's going to be the same for the acceleration. And if you want a little shortcut to find the acceleration, that, remember, is centripetal acceleration, just divide mass out of this. So 6,230 divided by 900. That gives you a centripetal acceleration of about 6.9 meters per second squared. That's about 2/3 of a g pointed inwards. Now in this situation, you have to think, what is providing the centripetal force? The only thing that is providing centripetal force, not on a bank turn, there's no rope or anything or wire connected here. Friction is. Friction is the force that's pointed inward. So it asks for the frictional force. The frictional force is the centripetal force. So these two values are the same thing. The frictional force, again, a centripetal force is not a different force. It's just the net inward force. What it's coming from depends on the situation. Here it's friction. Other problems it's been tension. In other problems it might be gravity. Okay, so here's the force of friction. All right, so we got everything here figured out except for the coefficient of friction. Now we have to recall back from a couple chapters ago. Remember that the force of friction, this is static friction, by the way, but since I just called it FF, we'll continue to do that, is equal to the coefficient of friction multiplied by the normal force. This is an equation from a few chapters ago. We said that the force of friction depends on the nature of the two surfaces in contact. That's what the coefficient tells you. And how hard they're getting pushed together. That's the normal force. Okay, we have the force of friction, and we have the normal force. When we solve for the coefficient, it just becomes the force of friction divided by the normal force. So 6,230 divided by 8,820, and that gives us a coefficient of about 0.7. And if you remember, the coefficient of friction is a unitless number and is just indicative of how slick or smooth the two surfaces are in contact with each other. I will give you another problem to do. I will write this on the assignment page on Google Classroom, but number 3 on page 11 is a little bit similar to this. And maybe I'll explain that one a little bit here. But a little bit different problem, but that will be the one I ask you guys to kind of do. Before we do that, one more problem I want to do, and this is something we talked about before, is the barrel ride. I showed you a video of this amusement park ride where people get stuck to the wall. It spins very fast and people get stuck to the wall. And if you remember, I said it works because friction holds you to the wall once the floor is removed. Friction now becomes so great because the normal force is the centripetal force. It is the net centripetal force. So here, just like the centripetal force was the force of friction over here, the centripetal force, and again, this is centripetal force, the centripetal force is coming from the normal force. So to get the centripetal force here, as we always do, you do mvt squared over r. When you do mvt squared over r, hopefully I don't need to write it for you anymore, that gives you 660 newtons. And again, I just found that by taking mass times this squared divided by that. So 55 times 6 squared divided by 3 gives you 660 newtons. That force has to be inward, and that's where the net force needs to be. That's also where the centripetal acceleration needs to be. To get the centripetal acceleration, and that's what that is, just divide the mass out of this, 660 divided by 9.8. That gives you about 12 meters per second squared. Now let's look at everything up here. Remember, the force of gravity is just mass times the acceleration of gravity. So 55 times 9.8 gives you a value of 539 newtons. And the force of friction needs to be supporting that gravity, because that's why the person's not falling, right? So the force of friction is also 539, because the person is not sliding up or down. The normal force, that's the inward force, so that's going to be the net force that we already calculated. Those two things are going to be equal to each other. So this is also 660 newtons. And the last thing, again, we have to figure out is the coefficient. So if you remember, force of friction, I'm not going to rewrite the whole thing, but you see this equation over here. We're, again, going to apply that equation as well as to this equation. Now for this problem, mu, that's that funny looking U thing, it's actually Greek letter for M, is going to be the force of friction, which in this case is 539 newtons, divided by the normal force, which is 660. And that so gives us a high coefficient of 0.81. And that's our last answer for that problem. So, after watching these notes, the assignment I would like to give you is, and again, I will list this on the assignment page, but is on page 11, numbers 3 and 4. And those are a little bit different than some of the ones we've done before. But I don't have those up on the screen right now, but I'll read for you 3. On 3, it says the coefficient of friction between a 1,125 kilogram car and the roadway is 0.85. That's the coefficient, that's mu. Determine the maximum speed which the car can maneuver through the curve with a radius of curvature 25 meters. Begin with the free body diagram. Okay, so basically on number 3, start getting that set up by, it confuses some people sometimes because it asks for the maximum speed, and so that's just referring to the maximum amount of friction that can give. Basically, the force of friction is equal to your centripetal force. Plug in the equations for both of those. So remember, the force of friction is mu times Fn. Again, this is for number 3 on page 11, is equal to mvt squared over r. Because remember, when we talk about the force of friction, that's always the maximum amount of friction that the road can apply. And so when we apply this equation, that it's telling us the maximum amount of friction, where if we solve for Vt, that will tell us the maximum tangential speed that we could go at that radius around. As is the case for each of these two problems, do them on your worksheet, take a picture of the work, make sure you show your work, and attach it to the turn-in page on Classroom when you're all done with that. As always, email or comment on Classroom if you have any questions. And then we're almost done with circular motion stuff here. We'll probably do a quiz in a day or so, and then we'll move on to gravity, which is the second half of this chapter.